Okay, for this problem, it might look like these two maybe shorted out somehow, or it's just got wire from one point to another that doesn't really serve any purpose. And like there's this junction here, and it really looks complicated when we look at this and how to just solve it looking at it. So we're probably best to, if we can, to redraw it. And redrawing this will actually make it look easier. So if we look at the ground point, we notice that it shares the common point from here with the bottom of this source, the negative part of the source, and the bottom of this inductor, and this point of the resistor R2, and this part of the capacitor X of C. We have R1 10 ohms, 60 ohms for X of C, 20 ohms for R2, and 80 ohms for X of L. Okay, and they want us to find the current flowing through the source. They want us to find the voltage across the inductor, and they want us to find the average power. So the average power is E by cosine of theta, where theta is going to be the angle associated with E, which is 0 degrees, and I, which we haven't calculated yet because we're going to find that from as I1. If I redraw this circuit, we end up with something like this. And I'll draw boxes with X of C here. That way it's a lot easier to draw, a lot quicker too. And so let me bring this one down so I have more room. This is R1, and here's our source. This is going to ground. And then from here, we have an inductor. Well, let's not draw that, let's draw the X of L. And that goes to ground. Resistor, inductor to ground. But then we also have R2. And that goes to ground. And X of C is connected to ground as well. And so now if we look at the circuit, these two are in parallel, and then whatever this becomes will be one value, and then that's in series. These two in parallel is in series with R1. So this total equivalent will be in parallel with X of C. So, because they share the same voltage point here. So if I redraw it again, we'll, let me put X of C here first, because that's going to be the top one. And then R1. And let's make this Z sub 1. Z sub 1 is equal to X of L parallel with R2. That's equal to R2 X of L divided by R2 plus X of L. Okay. And then so this is going to be Z1. See how now they're in series. Now I can add these two together. So let's make that Z sub 2. Z sub 2 is going to be equal to R1 plus Z sub 1. And then we'll redraw this real quick again. So, see that? We went from these two in parallel to this, these two in series to this, these two in parallel. This is going to be Z total. The total impedance that's flowing in this circuit can be calculated because it's a series parallel circuit that can be broken down to one element. If it can't be done with one element, it requires complex circuit analysis, mesh or nodal analysis, and superposition would be a problem where you would have two sources, and you can short one and solve the circuit with one shorted or open, depending on the circuit. If you have an inductor, or if you have a voltage source, two voltage sources, for instance, in superposition, and you short one, you're going to use one to do the analysis then first. Then you short one voltage supply, do the analysis, find the total current, voltage drops, do the same thing again with the other voltage drops shorted. But if you have a current source, you got to open those. So if you have a voltage source and a current source, you can still use superposition, but you're going to open the current source when you do that to that, and let the voltage source run, and then the voltage source will be a short. So that's good to remember for superposition. But this is the problem for just the algebra that gets you down to how to solve for total current. V1, if you notice, V1, if we get the current here, we know what the voltage is at for ZT. ZT would be this voltage right here. Voltage to ground, voltage to ground, voltage to ground. They're all in parallel, so it also shares the same voltage. And Z sub T will give us the voltage that we need, but Z sub T is these two in series. So we got to take the voltage drop across Z1. So we take this voltage, 40 volts, and multiply it by whatever Z1 is, and divide it by Z sub 2, the total impedance here, in order to get that ratio of the voltage. I'll write that down right here. V1 is equal to Z sub 1, which is equal to E times Z sub 1 divided by Z sub 2. Once we have the first step, getting the current, we can automatically solve for the average power, because we'll have that current in a phasor notation, which means we'll have a magnitude and an angle associated with it. If it was rectangular notation, it would just be most likely in parentheses the x and y value. The y value is always distributed with a j. The j represents the y-axis, negative and positive y-axis for a graph where you have reactances. So, in case of electrical theory. So, hope you like that. Okay, so now we're going to solve the problem using math. And just so we have everything we need, I'm going to write down each of these equations so that we have them. So Z sub 1, that's equal to R2 X of L over R2 plus X of L. Alright, and Z sub 2. Z sub 2 is equal to R1 plus Z sub 1. And then Z total, that's equal to Z2 in parallel. That's another way of saying it. In parallel, Z2 in parallel with X of C. These two ways of writing them are equivalent. These two lines represent the same thing as two things in parallel. So I could rewrite this as this, but with the X of C instead of X of L. So, just to keep things simplified, I'm going to save Z sub 1 value. The magnitude is A, and the direction it has in degrees as B. Same thing with Z sub 2. I'll do the same thing with Z sub 2 for the impedance for Z sub 2 will be C and D respectively. So if I do the calculation for Z sub 1, we'll get some value here. after that, then we'll calculate Z sub 2. After that, we'll calculate Z sub T, the total impedance. After that, we'll calculate I. So down here, we're going to say I T, which is equal to the I1 that we're looking for, will be E divided by Z sub T, because voltage is equal to the product of current and resistance. And so to find current, we divide both sides by resistance. The resistance goes away from that part of the factor, and then it comes over here. So, all right. So let's try to use this whole board to do this. R2 is 20 ohms at an angle of 0 degrees, and it's multiplied by 80 ohms at an angle of 90 degrees, because inductors have a 90-degree phase change in relation to an resistor. Resistors are always 0 degrees, and this is going to be 20 plus J80, and it's all in the product of ohms. I didn't write ohms in here. I could have, but I'd have to write it here and here. So instead, I wrote it at the end, so I only have to write it once to simplify things. But this requires the Pythagorean theorem, because the reason why is because when you plot these values on a graph, here's your x sub c, here is your x sub l, which this is going to be J 80 ohms. This is x, this is r, and so this is 20 ohms. We're looking for the magnitude of the hypotenuse. Okay, and if this is the hypotenuse, then I'm pretty sure if this is the angle we're associated with, then this would be the opposite side and this would be the adjacent side. But we're looking for the hypotenuse, and we use the Pythagorean theorem. And this theorem is a squared plus b squared is equal to c squared. And to find c, we take the square root of both sides. And this is the proof really of, oh yeah. Now this could be in either direction. This would be the positive x, and this would be the negative x. Positive y, negative y. Just think of that as a graph, and that's how we use the Pythagorean theorem. So bring this here. This is 1600 ohms squared. Ohms times ohms is ohms squared, plus at an angle of 0 plus 90 degrees, which is 90 degrees, and this is going to be divided by the square root of 20 squared plus 80 squared. So square root of 20 squared plus 80 squared. And I'll show it on the calculator. That becomes 82.46. And I'm going to use 3 significant figures. So 82.5 ohms at an angle of trig inverse. I'm using a trig function. So on this calculator, I have the trig function right here, right of my thumb. When I hit this, I get these options. And I want to take the inverse tangent. I'm going to take the inverse tangent of 80 divided by 20, or 4, because that's the same value as 80 divided by 20. And so if you notice, that's what I get. Okay, so we get 76 degrees, at an angle of 76.0 degrees. All right. But we still haven't found the total, because we got to divide the 1600 by 82.46 or 82.5. So 19.4. The impedance for Z sub 1 is 19.4 ohms, and this is just the difference of 90 minus 76, which is 14 degrees, an angle of 14.0 degrees. That's Z sub 1. All right, so what about Z sub 2? Z sub 2 is just R1 plus Z sub 1, but Z sub 1, let's take 19.4 and take take the trig 19.4 times the cosine of 14 degrees. We get 18.8. So Z sub 2 is equal to 10 ohms at an angle of 0 degrees plus let's see, 18.8 ohms and then let's do 19.4 sine of 14, which is 4.7 or 4.69. This is plus J 4.69. I'll just say 10 ohms. Just say 10 ohms. That way we're not having this in phasors and then this in, I forgot the notation. This is phasor notation, and I think this is rectangular notation. I forgot the name of this one, but they're different names of how you describe it this way. And I'd rather keep it consistent. So this is just 10 ohms plus this many ohms. And if you notice, this is equal to 10 plus this value. This doesn't actually add up to the J value. This stays the same. So we get 28.8 plus J 4.69, and this is ohms. Now we have this in that rectangular form. I think that's the right name of it, saying it, but if I'm wrong, you can correct me on it. But then we have, we can change this to phasor notation. So the square root of this value squared plus this value squared and it's good to make sure you know what your buttons you're hitting so you don't hit an error on the calculation. So the square root of all that, oh, I forgot to add the 28. So let's just go back and just change that 1 to a 2 in this huge calculation. It'll be a lot easier than going through all that again. Delete, press 2, enter. No, 28 by 2. Sorry. Yeah. This is equal to 29.2 ohms at an angle of, I'm going to take the inverse tangent of 4.69 and divide it by 28.8, we get 9.25 degrees. So that's Z sub 2. And we know that Z sub T is Z sub 2 parallel with XC. So now we can take, we can find the total impedance of the whole circuit, which is 29.2 ohms at an angle of 9.25 degrees, and multiply that by X of C, which is 60 ohms, at an angle of negative 90 degrees. It's negative because it's a capacitor. Capacitors have a negative 90 degree phase change with resistors, and 180 degrees phase change with inductors compared to inductors, so they can cancel each other out in a math problem. That would be a different problem one day. But here, we're going to add these together. We got to find the actual impedance of this. So 29.2 times the cosine of 9.25, 28.8. So we know what, we already know what that is. So we can just add this to the capacitive value. So the capacitive value becomes 64.69. So this is 28.8 plus, oh, not 64, it's negative 60 plus 4.69. So 60 minus 4.69. And that's a negative value. I said that wrong. It's actually negative 60 plus 4.69. But I'm doing that, I did that so I can get the, see, minus J of 55.31 ohms. It doesn't, you want to be consistent here, but whenever you do the calculation here for the phasor notation, it's always going to be positive because a J squared becomes negative 1, same as I squared, negative 1. And a negative times a negative is positive, so it's always going to be positive, no matter what, because of the Pythagorean theorem. And so when we do the Pythagorean theorem here, 28.8 squared plus 55.31 squared, 62.36 on the denominator here. And we have ohms, and this is at an angle of negative 55.31 divided by 28.8. That's it'd be helpful if I took the inverse tangent of that value. All right, we get negative 62.5 degrees. You can tell it wasn't a good value because I took the tangent of the negative 55.31 divided by 20.8 and I got negative 0.03, so I know that was wrong. It's 29.2 times the 60 ohms. We get 1752 ohms squared. I'm saying this really fast so I can get it done faster. Let's just add these together. Well, that's just really 80.75. I'm going to do 4 significant figures there because of that. It's right on the line of that. So 90 minus 9.25, 80.75, right? It's negative, okay. 1752 divided by 62.36. 28.1. So the total impedance is 21.1 ohms at an angle of negative 80.75, and we're going to subtract that from a negative 62.5, and that subtraction becomes an addition, but we still end up with negative 18.25 degrees. So we have the total impedance. All this just to find the total current. Now we can find total current. We did this first, right here. Then we did this, right here. And then we did this, CT, right here. Now we're going to find IT. IT is going to be equal to 40 volts at an angle of 0 degrees divided by 28.1 ohms at an angle of negative 18.25 degrees. Now 40 divided by that value, 1.42 amps. And that's at a positive value of 18.25 degrees. So here's our first answer. And the book says 18.26, but it's close enough. I probably did something with the calculation where I might have used, maybe I didn't use, maybe they used the simplified 3 significant figures all through it to do that, to make it 2 to the 6, I don't know. But that's the correct answer for the current, and just off by 1/100th of a value. But the voltage, now we can solve for V1, because we know that this total current's flowing through the total through Z sub t, which is the total impedance, and Z sub t is Z sub 2 in parallel with X sub c, and we know that the voltage is equal between Z sub 2 and X sub c because those are in parallel. So we can take the total voltage and divide that by Z sub 2 to get the total current flowing through Z sub 2. Okay, so 40 divided by Z sub 2, which is 29.2. It's 1.37 amps. Yeah, total current flowing through the total circuit makes 40 volts, and then 40 volts divided by that gives that current. 40 volts divided by that gives that current. Those two currents add to 1.42 amps. So the current flowing through the capacitor is actually 54 milliamps, and 1.37 amps is flowing through flowing through Z sub 2, and Z sub 2 is R1 plus Z1, so we know Z1 has that current, and so Z1, we just multiply this current 1.37 times Z sub 1 to find no, did something wrong. Oh, did a wrong value there. Times 19.4. So the voltage, I did this in my head pretty fast, but I'll show you what I did here. And I'll edit the video so you can see that the bottom circuit has 1.42 amps flowing through Z sub t. And then I'll show the second circuit above that one with, since they both are parallel, that voltage is going to be divided by Z sub t. And if we do both of those voltage drops, find a current on both of those elements and add them together, we get 1.42 amps. So that's a good indication that we're doing that right. So we get the current from Z sub 2, and then we look at the third circuit from the bottom, which is the second circuit from the top. There's only 4 of them. And the second circuit that was drawn shows R1 in series with Z sub 1. Whenever we have that same current there, that current is going to be the same for Z sub 1 and R1. So we know that that current is the same, which is 1.37 amps for Z sub 1. We multiply that by the impedance, and we get the voltage drop for Z sub 1. And Z sub 1 is X of L in parallel with R2. So we get the voltage drop for X of L. That's the voltage we wanted. And that value is 26.57 volts. V1 is equal to 26.57 volts at an angle of, well, 14. Let's see, the current, let's see, we gotta make sure the current's right on this, or the phase angle's right on this. So we took 40 and we divided that by Z sub 2. Z sub 2 has an angle of 9.27 degrees. So 0 minus 9.27 is negative 9.25. That value is multiplied by Z sub 1 to get the voltage drop across the X of L. And we take negative 9.25 and we add that to the 14, and we get 4.75 volts, or not volts, degrees. So this is the answer for the second one, V sub 1. Now the average power is equal to voltage times current, VI or EI in this case. And the average power in this case is going to be equal to I cosine of theta. Cosine of theta is really the value of E degrees plus the value of I degrees. And the I degrees here is 18.25, and 0 is for voltage. So we don't have a phase for voltage. We just have 0. We do, but it's 0 degrees. We take 40 volts at an angle of 0 degrees, multiply that. Well, let's just do magnitude without direction. 40 volts times 1.42 amps times the cosine of theta. Theta is going to be 0 plus 18.25 degrees. All right. And so our power times 1.42 is 56.8 amps times the cosine of 18.25. 53.9 watts. That's how much power is being drawn from the whole circuit. This is the total current flowing through the circuit. And across the inductor, this is how much voltage and how much phase change it is compared to that. What this represents is it's really close to 0 than it is to 90 degrees, which means most of most of the power is being drawn from the resistive load, well, from the resistors. So it really can't, I can't say much about how the capacitive and inductive loads are interacting here because I don't know the specifics of that. I just know that do the math problem here. Hope you like that.